Welcome to this lesson on the fundamentals of voltage. Today we'll explore the concept of voltage, what it represents in a circuit, and how a battery generates the push that drives current through electrical components. This foundation is essential for understanding how energy is distributed and managed in any circuit. Let's start with the basics. Voltage is a measure of electrical potential difference and is quantified in volts. While voltage describes the concept of potential difference, volts are the unit we use to quantify it. Think of volts as the measure of the push that drives the electrons through the conductor. For example, a 9-volt battery has a higher potential to drive electrons than a 1.5-volt battery. The presence of voltage creates an electric field within a circuit. This electric field exerts a force on electrons, causing them to move and generate current. Without voltage, there's no electric field to drive electrons forward, which means no current can flow. Now let's look at the battery as a power source. In this setup, the battery supplies the voltage or electric potential difference that drives electrons through each component of the circuit. This includes elements like the fuse, wires, switch, and LED. The battery acts like a reservoir of potential energy, ready to drive electrons through the circuit once we complete the path by closing the switch. Here we have a simple circuit consisting of a battery, a latching switch, an LED, and wires. The multimeter is measuring the voltage at the battery terminals. As you can see, the multimeter reads roughly 12 volts. This voltage is present whether the switch is off, leaving the circuit open, or when the switch is on, completing the circuit and allowing current to flow to the LED. First, with the switch in the off position, the circuit is open. This means that although the voltage is present at the battery, no current is flowing because there is no complete path for the electrons to travel through. The battery maintains its potential difference, or voltage, at about 12 volts, ready to push electrons if the circuit is completed. Now when we turn the switch on, the circuit is closed, and current begins to flow. The LED lights up, indicating that electrons are moving through the circuit. However, notice that the multimeter still reads close to 12 volts. The voltage at the battery terminals remains stable because the current drawn by the circuit is relatively low. In circuits with low current demands, like this one with an LED, the battery voltage remains stable and does not drop significantly. However, consider a car's starter motor. When a starter motor is engaged, it draws a large amount of current to crank the engine. This high current demand can cause the battery voltage to drop momentarily due to the battery's internal resistance, limiting how quickly it can deliver energy. In this circuit, the current draw is minimal, so the battery voltage stays nearly constant. This demonstration illustrates two key points about voltage. Voltage is present at the battery terminals whether the circuit is open or closed. In circuits with low current demands, the battery voltage remains stable and does not change significantly. However, larger loads like a starter motor can cause the battery voltage to drop temporarily due to the high current demand. This stability in voltage ensures that the battery can power components in the circuit under normal conditions. In future lessons, we'll explore how varying current demands affect battery performance and how to identify voltage drops in high current situations. So, how does a battery establish this voltage? Inside, a chemical reaction converts stored chemical energy into electrical energy, generating free electrons and building up an excess concentration at the negative terminal. Since like charges repel, this excess creates a natural drive to balance out by moving to a point of lower concentration. in this case the positive terminal, which has fewer electrons. To help illustrate this difference, we've shown a simplified image where the negative terminal has a high concentration of electrons and the positive terminal appears as if it has no electrons. In reality, the positive terminal still contains electrons, just at a much lower concentration than the negative side. This difference in electron concentration creates the potential difference across the battery, which is what we measure as voltage. Think of this as a difference in potential energy, commonly called potential difference. The higher the difference, the stronger the electric field that drives electrons through the circuit. With this potential difference established, we can now measure the battery's voltage across its terminals. This measurement reflects the battery's ability to drive electrons from the negative to the positive side, revealing its pressure or capacity to do work. Here we have two batteries side by side, both connected to voltmeters. The battery on the left shows 8 volts, while the battery on the right shows 12 volts. Both batteries have a difference in electron concentration between their positive and negative terminals, which is what creates voltage or potential difference. In the battery on the left, we see fewer electrons concentrated on the negative terminal compared to the battery on the right. This smaller difference in electron concentration results in a lower voltage, which the meter displays as 8 volts. While this battery still has potential to do work, it's less than the potential of the battery on the right. Now on the right, we see a higher concentration of electrons on the negative terminal, creating a larger potential difference between the terminals. This greater difference results in higher voltage, shown on the meter as 12 volts. A higher voltage means this battery has more potential to push electrons through the circuit and do more work. This comparison demonstrates how potential difference, or voltage, changes with the concentration of electrons at the negative terminal. A higher concentration of electrons creates a stronger push, resulting in higher voltage. This principle is key to understand how batteries store and deliver energy. Before we wrap up, it's important to distinguish between voltage and capacity. While voltage represents the ability to push electrons through a circuit, capacity relates to how long the battery can maintain that voltage over time. A small set of AA batteries and a large car battery might both provide 12 volts, but the car battery has a much greater capacity, allowing it to power components for a longer period. We'll cover capacity in depth later, but for now remember, voltage is about the push that drives the electrons, while capacity is about how long that push can last. Now let's take a look at measuring the voltage of different batteries using a multimeter. We'll start with a standard AA battery, then a 9-volt battery, and finally a 12-volt battery. By measuring each, we'll see how the multimeter displays the potential difference, or voltage, across the battery's terminals, reflecting its energy potential. First up is the AA battery. We'll set the multimeter to the appropriate DC voltage range with the black probe on the negative terminal and the red probe on the positive terminal. We get a reading of around 1.6 volts. Since AA batteries are typically rated at 1.5 volts, this slightly higher reading indicates that the battery is fully charged and ready for use. Next, let's measure the 9-volt battery. Again, with the black probe on the negative terminal and the red probe on the positive, we're seeing a reading of around 9.5 volts. This is a strong reading, slightly above the nominal 9-volt rating, which shows that this battery also has a healthy charge. Finally, let's check the 12-volt battery. Placing the black probe on the negative terminal and the red probe on the positive, we're getting a reading of around 12.4 volts. This slight increase over nominal 12-volt rating shows that this battery has a strong charge as well. These measurements give us an indication of each battery's charge level and general health. For example, a AA battery reading of 1.6 volts, the 9-volt battery reading of 9.5 volts, and the 12-volt battery reading 12.4 volts all suggest that these batteries are freshly charged. However, voltage alone doesn't fully verify a battery's ability to supply power under load. To thoroughly assess a battery's conditions, factors like capacity and internal resistance would also need to be evaluated. In this video, we talked about voltage as a fundamental concept that underpins all electrical work, whether it's driving a tiny LED or powering complex systems. Voltage serves as the electric potential difference that initiates current flow. Understanding how this potential difference works, especially within a battery, gives us a foundation for grasping more complex topics in electrical circuits. In the next lesson, we'll look at how these principles apply to practical circuit setups.